I've been using this tool Windsurf to help with development at my current job. And so what I wanted to do though is try this on a type of algorithm that's much less common, so there's a lot less information out about it. And this is also something that I know really well. So the paper that I'm going to try and replicate here is an approximate Riemann solver for the two-fluid plasma model. I've done this several different times. I did my master's thesis on this. And actually I got this to work with Windsurf. It took quite a long time to do. So I did create a repo here which actually has the working model. And I'm going to then try and go through some of this again so that you can see some of how it's done and some of the problems that you encounter doing this. So I've cleared it out, starting a new conversation. I'm using Claude 3.5 Sonnet, and this is what Windsurf looks like, right? It's just the regular VS Code IDE, but their own version of it. And you have the chat bar on the side here. Some of the things that I've already put in here, because I've run through this several times to figure out how to get this to work best. I use poetry, Python poetry, but more importantly, I put in two things in here. One is initial conditions, which I took from work that I had done previously, is just so it knows the type of problem that I'm solving, then the constants. And actually what I should say is what I'm trying to get out of this paper is I'm trying to reproduce the plots that are down here. These are shock, specifically, this is the one that I'll be interested in. And I was able actually to do that. Some of these look a little bit different, but these are essentially right. A lot of it depends on the flux and various things and the resolution you choose about how similar to this it's actually going to look. So we're going to start here, and I'm going to be asking it to solve this problem. So I want to create an approximate Riemann solver for the two-fluid plasma system. I've put some hints in the hints directory of this repo, so you can use that to develop initial conditions, etc. Okay, we're going to just start with that and see what it does for us. Okay, I'm using Claude Sonnet. This I found is the most useful. So it's looking at this. Okay. Okay, I paused it for a second while I ran through and did a bunch of generations. So this is my initial statement up here, and then it's doing all these checks. It's creating, it doesn't need to create the requirements.txt. So I'll just tell it that. And I'm going to just say, I don't need the requirements.txt as this is a poetry repo and all the dependencies are already installed. And then I'm going to say one more thing. Oh, and I forgot to tell you everything should be written in PyTorch. Let's reject that installation, and then it's like this. Okay, so it generated a whole bunch of stuff. It took maybe a few minutes to do that. And so what it did here is it's modifying things to use PyTorch and stuff, and still added these different files. This is going to ask me to do this, which isn't going to work. but let's take a look and see what it actually put in here. So it created this constants file. Okay. It created a Riemann, two-fluid Riemann solver. And so it looks like what it's doing here is initializing a shock right here. It's computing fluxes, and I don't know, let's see here. Some of these look like they're right. Let's see. Electron fluid. I don't know why it's using an EIN sum here when it doesn't necessarily need to. And then, all right, well, let's just look at this and see if it's right. So let's accept all changes. Then I'm going to accept all here. And here I'm going to say reject. The above, nope. The above command will fail. There is already a .v in the directory, so use that Python to run. So that's what I'm going to tell it to do, so that we can actually run this. That may not run. I'm not sure that's going to run. That would in a normal case, but for some reason this, okay, it did in this case, and now it found an error with the EIN sum. So it's actually going to try and fix this, so it's editing it. Now let me see, while I'm looking at this, let's see if it's actually done any time integration. So it's got a state, it's got a flux computation. Oh, it's got the local lax flux. Depending on how it does that, it could be hugely diffusive. Like you really want the flux to be applied to the fluid model separately from Maxwell's equations. Okay, I'm going to accept all changes here. And anything else here? Just accept all. Now we can run this again. You don't have to accept the changes to make it run because it's already made those changes. So it's going to find more errors here. What does my main file look like? Okay, it's just a loop, and I wanted to solve. Okay, moving to the CPU for plotting. So this one's, it's also written some plotting routines. The time integration, let's see what that looks like there. So this step, so it looks to me like it's doing a very simple, I'm not sure exactly what that step is right off the top of my head. But it looks like it's doing a two-step. So maybe this one is actually stable. All right, accept and run. I'm going to accept that. Accept. So it's got more indexing issues that it's run into. All right. See what it's going to say here. My goal here is not to actually edit any of this and make it do it. entirely on itself just with advice from me. Okay, it actually ran. I'm gonna just accept all. And let's see, where did it actually write out all the data? Okay. Let's see here. Two fluid results. Well, it created this file here, and these results are completely wrong. Okay. So, but let's see, the initial conditions look like they might actually be correct. Okay, but I'm going to tell it to do this. Create a separate directory to store results. Store them with just the iteration number as in with just the iteration number. And let's see here. Also, make sure you are using a TVD wrong Dakota times stepping scheme. And I'm not sure if it had source terms or not. Save results at 10 different time steps. Current results are obviously wrong. Okay. So now it actually knows something there may be incorrect. All right, you can make that directory. So it's updated Riemann solver. I'm gonna trust it. That looks like a Runge-Kutta method. Okay, let's run it again. Accept those changes. Also modified main.py, but I don't really care. I'm going to accept them. And let's just accept all. Don't know if constants changed. So it's got a new directory here. That's the initial condition. Cannot convert CUDA 0 device to type tensor. So it's going to make sure it does that. So the initial conditions, these look like they're actually matching what I want. But a different thing is I want it to plot number density. And I should also have it plot pressure and velocity. Yeah. So I'm going to reject that right now. Let's just say stop. Change the output to plot to also plot to plot number density instead of mass density. Also plot velocities and pressures. So then we'll have a, okay, so it's finished writing. I'm going to accept and tell it to run this. It's got more errors. So now it's going to try and fix those problems. I need to fix the device handling and the primitive variable computation. So it's made those updates. Let's try it again. Okay, so now it's running again. We have number density. Yep, we have both electron and ion, and then we have the velocities here. That's good. Now, this. Okay. I think I'm wanting it to write more than this. Okay, this is taking too long, so I'm going to ask it to make some changes. Reduce the resolution of the simulation so it runs faster, say 200 cells. Okay, so that should hopefully, I don't know if that's going to make enough of a difference. And then actually I'm going to also make one other change. Also, double the CFL. Minimum time step should be the minimum of the CFL condition and the plasma frequency. It's right now using the plasma frequency. I mean, excuse me, it's using the speed of light, but there's a plasma frequency which can dominate, and it shouldn't be in these problems if the resolution is high enough. Okay, I'm going to run with the new updated conditions. And then found an error. Okay, so it's editing again. See if it works this time. If you run everything in this window on the right, then it sees all the errors and it can edit them. If you run it in your own window or your own terminal, then it doesn't get all the results. Okay, so now it's doing that. So the time step is being adaptively computed. Good. Right. Okay, you ran the simulation, but It seems to have stopped at one time step. So it didn't actually produce any results. So I put in another bug in the code. Should modify this one here. Okay, you're right. Let me add some progress printing to see what's happening with the time step. Okay. So it starts putting in these debugging statements, and then it can read everything. It can read those things itself. Accept all. I am going to accept. Let's do that. Oh, it's got some nans. So it's adding nans. It's going to do some diagnostics, but I'm going to look and make sure that it's doing source terms and everything the way it should be. Okay, now I think it's hasn't put in source terms. Doesn't seem like it. What are some other things I want to make sure that it does? Also make sure you are using copy boundary conditions. Otherwise, you might be getting problems at the boundary. So we're going to stop that and run it now. It says, yes, I need to add the source terms for the electromagnetic forces and implement proper boundary conditions. Let me update the solver. Well, most likely it also needs to put in current sources for the electromagnetic fields, which it probably hasn't done, but we'll see if it does it here. Okay, so now it is added the source terms here. So it's added this thing called compute source terms. And I think this is actually right. Yeah, that looks correct. This is the energy equation, so that looks like J dot E. And then it looks like it's also doing the same thing here, but it looks like it hasn't done the electromagnetic energy source terms. Forgotten the source terms for the electric field equation. Stop that, like that. Like I said, it's adding all these to some gigantic flux. So my feeling is if it's treating everything as a giant flux and using the lax flux, then there's a good chance it's using the speed of light as the diffusion parameter, and that's going to be really slow, or it's going to be really diffuse. So I'm going to accept all these changes. Let's run it and see if we get any errors. Yep. So it's found another error. It's got some issues with the array. So now it's going to try and fix those. Okay, it's modified those codes, so let's run it again. Okay. Well, clearly it should know that it has an error here. I'm going to just accept everything. Okay, so it clearly got an error and then it didn't bother to fix it. Alright, so yes, there's an issue with the tensor dimensions. In the cross product calculation, let me fix the source terms. Alright. Okay, I've accepted all changes and now it wants to run again. See if we get another error. Oh, a bunch of nans are being detected. Okay. Looks like we're getting NAND values after a few steps. Let me add some diagnostic output to see what's happening with the state variables before they become NAND. Now I know that I've gotten this to work before, so I might have to look at it a little bit to see what I think it's forgotten here, but we'll see what it actually thinks. Okay. Sure, let's do it. Go ahead and run it. So it's gotten NANDs after 4 steps. Yep, so it says the electron velocity is growing extremely rapidly from 0 to 8,000 in just a few steps, which is causing the electron energy to explode. This is happening because the electron mass is much smaller than the ions, making the electron much more responsive to the electric field. Let's add some limits to prevent. Nope, I don't want you to do that. Nope. Mass difference is correct. Double check your equations and make sure you are using a local lax flux. The electrons should have their own lax flux. The ions should have their own lax flux and EM field its own. There should not be a single lax flux for the entire system, which is what I think you are doing. Okay. So actually, it would be better if I could talk to this guy, because I can talk faster than I can type. But this is what has happened before. It runs into these problems and it thinks that there's some other issue, like, okay, the issue is the electron velocity going up or something like that. And yet we know this algorithm works, and I've gotten it to work before using Claude, but then it will get stuck going down a rabbit hole that's completely wrong. I don't have time for that, so I'm telling it what I think what some of the problems probably are. Okay, here's a funny one. Now let's run the simulation with the correct flux calculations. Okay, let me also fix the compute fluxes method to properly handle the staggered grid. Ah, it's mixing up concepts. No, I don't want a staggered grid. This is an approximate Riemann solver. It does not require a staggered grid. Okay. This approximate Riemann solver does not require a staggered grid. Okay. So yeah, this is funny. This is another thing that I've seen happen. Didn't happen the last time I did it, but it mixes up various different concepts from different solvers that it's seen. So if you don't provide enough detail, then it may write your equations completely wrong in like a jumble of MHD, single fluid MHD and two fluid and things like that. So this one may all be going off, you know, any more of these, except okay, good. Now it's seeing some problems here. It's seeing a bunch of its own problems and trying to fix those. Ah, there's a dimension mismatch. At least I trusted on those. All right, let's do that. Run it again. Okay, so now it looks like it's running. Oh. But we're getting a lot of nans here. Curious what else it used for its explanation up here. Ah, you're right. For approximate Riemann solver, we want to compute fluxes at the cell interfaces using states from adjacent cells. Let me fix that. That's funny. Yep. So it's got all these nans. I see the issue. The simulation is becoming unstable due to the very high velocities and energies that are being developed. This is likely due to the source terms becoming too large. Let me add some limiters. Ah, you know what's going on? No. I'm gonna say this. Okay, that's a really bad idea. Your that's a bad idea. Also, this method should be second order accurate, so you use flux limiters. Use the min mod limiter in particular. Okay. So now it's going to go analyze this again. Okay, so now it's made a bunch of changes here. It says it's added a min-mod limiter. It's modified the flux computations, use second order reconstruction, updating the RHS computations. Okay, I'm going to accept all of these. Accept them all. Okay, I'm going to ask it this. Should we run it again? Now, of course, I'm expecting it to just, yeah, let's run the simulation again to test the new second order scheme. That's a good idea. Okay. Okay, so I'm wondering if it's gone out of the context window and say, no. No, remember, you need to use the Python in the local.vnv file. So yeah, it asked me a question that it already knew the answer to. So either there's data that has gone out of the context window and it forgot the first things that we ran into, or something else along those lines. So, oh, there's a problem right there. Okay, so in the Riemann solver, this is again another issue that this thing tends to have is, since I'm using torch, it's going to look at the source terms here. Oh, geez. Yeah, so it's probably, the source terms are probably completely wrong. Let's see here. State slopes. Source terms. Actually, let's just look for this. Gradient. All right. Oh, that is funny. No, your source terms are completely wrong. Okay, so it's adding source terms, a gradient of BZ. It should be done as a flux. Okay. Gonna stop this. Your electromagnetic source terms are completely wrong. They should just be current, not gradient, not torch.gradient. We are implementing an approximate Riemann solver, so the all the EM components are in the flux, which is computed using a finite difference. Do not use the torch gradient calculations anywhere. Okay, now I don't know if that's I don't know if that's gonna say, you're absolutely right. I apologize for the confusion. The electromagnetic component should be handled by the flux calculation. The source term should be include only the current terms. Okay, let's see if it does this properly. Yeah, it's done it. JXJYGZ. Yeah, that looks good. So this might be part of the problem. Of course, if I have to look, oh, so now it might be working. Let's take a look at the results. Okay, where is it actually? This could be right. Potentially. That density spike there, that's not a good sign. So but it could actually be right. Let's see here. It could be right. Looks like it had another data dump. Nope, it looks like the everything is crashing. So this isn't, there's still something wrong here. Okay. And then, so I'm going to ask it to stop this. Okay, I'm going to tell it, it's trying to do all of this stuff. All these limiters that it's adding on, it says, okay, we're still getting numerical instabilities. Look at the output. I notice a few things. The time step is being limited by the plasma frequency getting very small. We start there. The electron density. Okay, this suggests that our source terms for the electrons might be too strong. Let me check the current density limiter. Okay, first of all, if you start putting in these limiters in all different places, then you can get really bad results. Okay, so I'm going to tell it, please don't use, please. Flux and slope limiters are required, but if you start limiting other parameters, then you're gonna get all sorts of strange issues. The one caveat is you can limit minimum density and pressure. But with enough diffusion, this shouldn't be an issue. Although so consider, okay, look at the rest of your equations and see if you see any errors. You're right. I apologize for going overboard with the limiters. Let me review the equations, focusing on the core physics and numerical scheme rather than trying to artificially limit values. Okay. So now it seems to have found a few errors in its code. Wrong. U0 is already mass density. No, so that's correct. If that's a mass density divided by mi, that's Ni. No. Let's see here. Okay. We have limiters and current density limiters that we should remove as your advice. Okay, good. We're adding density to energy, which doesn't make physical sense. Let me fix these. Okay, I'm confused. I'm concerned about what it's trying to do here. Key changes made. Okay. I'll accept them all. Accept. Oh no. Yes, I'll accept. Okay. Oh, now the number density is absolutely gonna blow up. I think, if it's already gotten there. Surprisingly, the time step is not. Okay, I mean, that looks okay. But this one's obviously wrong. Alright. Okay. Epsilon naught. J or epsilon naught. So it's got c squared j. In this case, because of the way I did the normalization, it probably won't work. Okay, and now yeah, this modification. Okay. Actually, negative j or epsilon not. Double check your signs and rest of your equations. Okay, so I want to know if the flux is right again. Compute flux. That's saying I've added negative sign to the electric field source. If this correctly represents it, it's consistent with the physical picture. The electric field tends to be reduced by the current it drives, a form of screening effect in the plasmas. Okay, I'll accept all, and then let's run it. This is how it implemented the mid-mon limiter. Again, nope. Remember you need to use the Python in the .vnv. Okay. This is taking a while. Okay, it's finding some of its own issues again, and it's trying to fix them. Okay, it's running it again, so maybe I'll get some results here. Here's the first case. This time it doesn't seem to be printing anything out. So now it's getting a bunch of nans. This is looking not bad. I mean, it does look bad, but at the very beginning, that looks okay. So I see it getting numerical and space leading nan. Initially, the step CFL at DT2. Time step becomes limited by the plasma frequency rapidly decreasing. The values of the solution start growing exponentially. Change in the E field source term sign J appears to be physically correct, but the instability suggests we might need to add some form of numerical dissipation or filtering to control the high frequency rush. Implement a more robust time stepping scheme for stiff source terms. Consider splitting source terms. Would you like me to try and implement these potential sources? Okay, I'm going to look at what it's done. Actually, how about this? Make sure you are using a TVD time integration scheme. So what I'm going to tell it, and then it could be doing something wrong with the so it's got fluxes. Local lax flux. Okay. Electron fluxes. EM fluxes. Okay. So it claims that its Runge-Kutta RK3 implementation is incorrect. But our current implementation has the wrong coherence in the third stage. Let me fix this. Okay. Do you believe it? Let's try it. I mean, maybe I can ask it to use a second order method, but before it's gotten this correct. Okay, it's going in circles here. It's thinking again that it needs all these maximum electric field stuff. And I'm going to say it has something else implemented incorrectly. No, you don't need that. Reject. No. No. You don't need those modifications. No, I want it to stop. So it keeps on editing this stuff. No, you don't need those modifications. You actually solving, are you actually using an approximate Riemann solver? Are your initial conditions correct? You can pick a minimum density, number density, and pressure of about 1 divided by 100th the initial density and pressure, and use that as a basement. But you need to make sure energy is modified appropriately when those limits are hit. So let's do that. But it's trying to add a whole bunch of things. So I can't really keep up. Oh, look at this. It's adding scaling. I'm going to scaling to the electric field source. No. I don't think I've ever had to limit the electric field when I've written any of these solvers. So I don't know how much longer I'm going to do this for. I've gotten this to work once before, and I don't think I have the patience to get through all of this stuff. Let's see if it still added these e-scaling. Oh gosh. Okay. Let's go like this. The e-scaling. Pause here. please get rid of the E scaling and any other hacks like that you've put in the code. Yeah, I'll remove the artificial scaling and limits from the source terms and let the physics evolve naturally. Let me check the current source term implementation. I'll remove the artificial limits and let the physics evolve naturally. Okay, I removed artificial limits or scaling. All right, accept all. And let's do it again. Let's run it. Oh, it's telling me no module named torch again. It's great. Please use the Python in the .venv. Stop that and then accept this. Okay. Accept. Okay, I'm done. I got it to work once, and this second time I am not. It's telling me the electron momentum terms are blowing up first in the electric field terms. Let me check the flux computation. Okay. Yeah, he's going to check the terms he just added. I see the issue. I made several mistakes in the flux computation. The pressure term should be added to the momentum flux in tensor form. The Lorentz force shouldn't be in the flux. It's already in the source term. Yes. Yes, it was in the flux. That is very wrong. The M-field indices were wrong. Okay. Let's run it again with these fixes. Okay, let's try. Accept all these changes. And let's accept this. Maybe we'll actually get it. Well, I still see looking at the output, the electron momentum terms are going to infinity first. Let me check the source terms and make sure we're handling the electromagnetic coupling correctly. Okay. We're not handling the magnetic field evolution correctly. We need to add the curl. Uh-oh. 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 Curl of E to the magnetic field source term. No. No, 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 no. Okay, so it's getting too confused, and this is just going to take me, forever. Okay, that's it. And so you can actually make this work. I did it once, but I guess I could do it once and 4 times. So that's it for me.